Hello everyone, I'm Shushu from Computer Hardware and System Evolution Laboratory, Peking University. Today, I'm happy to introduce our work ScalaAFA, which is a user-space all-flash array engine with holistic designs. The last decades has witnessed all-flash arrays or AFA increasingly adopted as buffer layers in data centers and supercomputers for its attractive performance and reliability. Lots of vendors have launched their own AFA products, such as Dell, PureStore, and NetApp. However, with the continued advancement in SSD technology, current AFA risks becoming a bottleneck for future storage systems. To be precise, most AFA engines are designed for low-speed storage devices, whose maximum throughput is about 500 megabytes per second. But the bandwidth of emerging PCIe 5 SSDs can achieve 13 GB per second. So how can AFA engine better leverage these high-performance SSDs has become a critical problem of designing next-generation storage systems. Considerable efforts have been expended to make AFA more practical. We classify them into two types, strip write and two-phase write, based on how data is written to SSDs. Strip write AFA, such as MDRead, the default AFA engine in Unix kernel, have been widely used since decades ago. However, it suffers from partial write issue. Specifically, when the write data size is smaller than the strip, the AFA engine must read the missing data belonging to the same strip out. Then, the host can calculate the parity for this strip. Finally, both data and parities will be written back to SSDs. Partial writes introduce extra rate and intensive parity updates, which significantly delay the I/O. Tackling this issue, two-phase write AFA uses replication as a stepping stone to the stripping. In the replication phase, data chunks are replicated into n+1 copies to provide the same fault tolerance as strip write AFA. When the size of replicated data exceeds a given watermark, or user I/O are delayed and the conversion phase starts. In particular, the host reads all data of the same strip from SSD and computes the parity. Then the data and the parities are written back to SSDs. In the stripping layout, as in the strip write AFA, finally, the space used to store the replicas will be recycled. Two-phase write AFA usually exhibit better throughput and latency. Therefore, in this paper, we focus on optimizing the two-phase write AFA. If you are also interested in strip write AFA, you can refer to our prior work, ScalaRead. So, can existing two-phase write AFA adopt high-performance SSDs? We conduct an evaluation on Fusion Read, one of the sorter work with 4+1 Samsung 980 Pro SSDs. Construct 5 SSDs at RAID 5. Unfortunately, it's still the bottleneck. The right figure shows the sequential write throughput and the CPU overhead breakdown with different numbers of I/O threads in replication phase. Fusion Read achieved only 37% of ideal performance with one thread. This is because the frequent context switches and the tedious storage stack consume tremendous CPU tricks. While I/O only accounts for 21%. Even worse, extra threads cannot lead to scalable performance because of log overhead. In fact, we even don't have that many CPU threads available in real AFA products, as the CPU thread to SSD ratio is usually 1:3. All in all, the software overhead imposed by the tedious storage stack has become the bottleneck for achieving high performance with limited CPU resources. The performance becomes worse when the conversion phase starts. As shown in the figure, when the conversion phase starts, write throughput drops from about 4.8 GB per second to about 500 megabytes per second. To explore why, we break down the CPU overhead and find that the time consumed by the conversion task in the background dominates the conversion phase, as shown in the read part in the figure, while user I/O only consumes 24%. We further categorize the conversion overhead into read, write, and XOR operations. Result shows that The host to SSD read and write communication is the main overhead. This is our second challenge. Apart from the aforementioned penalties, two-phase write AFA impose two more challenges. First, to support out-of-place updates, AF engine maintains extra mapping tables in host memory to record where data is stored. As these mapping tables are updated frequently, processing them imposes a huge burden on the host. Second, the replication plus stripping write causes significant write amplification, which shortens the lifetime of SSD. Tackling these challenges, we propose ScalaAFA, a holistic design of AF engine that can extend the throughput of next-generation SSD arrays in scale with low CPU costs. We incorporate ScalaAFA into user space to lighten software overhead, considering lock-free principle of user space storage framework, such as SPDK. ScalaAFA replaces traditional locks with an efficient message passing-based scheme to facilitate inter-thread synchronization. In response to the CPU burden imposed by background conversion, ScalaAFA proposed to offload these tasks to SSDs, thereby leveraging the SSD built-in XOR engine to generate parity, to mitigate host and SSD communication overhead in the offloading. ScalaAFA takes a novel data placement policy that enables transparent data gathering and in-place parity computation. In the face of frequently updated mapping tables, ScalaAFA uses a hardware-based crash consistency mechanism, significantly reducing the software overhead. Finally, to temper the damage of write amplification on SSD lifetime, ScalaAFA utilizes the SSD internal high-endurance write buffer to accommodate transient writes. Let me first introduce the storage space abstraction of ScalaAFA. Similar to conventional two-phase write design, there is an indirection layer between the user address space and the SSD logical address space, which converts random write to sequential writes. ScalaAFA partitions the storage space of SD into two areas, transient area and normal area. The former is used to store transient data, while the latter accommodates long-term data. In the transient area, continuous K chunks in the same SSD make up a vertical hero, or named VH, while in the normal area, K plus M chunks with the same SSD logical address from K plus M SSD are grouped as a horizontal hero, or HH. Further, ScalaAFA composes one HH and M VH as a hero group, or HG. For simplicity, in all examples of these slides, we set K as 3 and M as 1. That is, construct a RAID 5 with 4 SSDs. With the abstraction of HG, ScalaAFA can track storage location of data and parities by associating strips with HGs. To enable multi-thread access, we have to prohibit threads from placing different data on the same SSD address concurrently. In other words, ScalaAFA has to manage the write permission of SSDs. ScalaAFA achieves this with a centralized space manager. Initially, all write permissions of heroes belong to the space manager. When an IO thread is set, it asks the space manager for heroes. Then, the space manager grants heroes in batches. Afterwards, if an IO thread wants to write data chunks to a certain user address, it first assembles granted heroes as an HG. Then the data will be written to the HG, and the user address will be mapped to the corresponding strip. The space manager can retrieval heroes when IO thread is being disrupted or conversion phase is conducted. Please refer to our paper for more details about the grants and retrieval scheme. So, how can ScalaAFA offload conversion tasks to SSDs? We illustrate this with an example. In the replication phase, if one data chunk is written to the strip, it will be replicated m plus 1 times, 2 times here as we set m as 1. One of them will be stored in HH, while the other m copies are written to the VH. Repeating this process, data chunks belonging to the same strip will be transparently gathered in VHs, such as these chunks. So afterwards, when the host is idle or VHs are running out, ScalaAFA starts conversion phase and offloads the conversion task to SSDs. Specifically, the host needs to send a customized NME command to SSD, which describes the conversion task. Once receiving this task, SSD conduct conversion locally. Specifically, SSD controller read chunks to its internal DRAM. It then computes the parity chunks and write it back. Finally, the SSD cleans the data in VH by marking the flash pages as invalid. Note that the parity computation can be done with the available SSD internal XOR engine, which is originally used to compute die-level parity within SSDs. To support out-of-place updates, ScalaAFA maintains two mapping tables in host memory. As these mapping tables are updated frequently, persisting them imposes a huge burden on the host, by redo log or undo log. So, how can we persist them with low cost? We achieve this by utilizing SSD out-of-band area or OOB area. OOB area is the part of flash page that used to store metadata, such as ECC, and usually invisible to users. However, OOB is scattered across different flash pages with a size of tens of bytes. It's difficult to store the entire mapping tables in one OOB. To better utilize the limited OOB, we first convert mapping tables to a segmentable data structure called persistent mapping table. Note that each row in the persistent mapping table is corresponding to a SSD logical page or SSD LPN as shown in the last column in the table. Since logical pages are one-to-one mapped to physical page in SSD, we can slice this table on SSD LPN and store it in the corresponding OOB. Specifically, we piggyback the sliced metadata in write request and persist it to OOB with flash program operation. Note that writing data and its metadata in the data and the OOB area can be done by a single flash program operation. The cost is minor. Then let me introduce the evaluation result of ScalaAFA. We implement ScalaAFA in SPDK and use FEMU, a popular QMU-based emulator, to evaluate our hardware modification on SSD. We configure the emulated SSD as high-performance storage devices with 7 GB per second and 5 GB per second read and write peak bandwidth, respectively. We also get configurations of the XOR engine from an Xilinx FPGA. It takes 20 microseconds to calculate a 64 kilobyte parity chunk from 6 data chunks. We compare ScalaAFA with 5 SOTA popular AF engines, including both strip-write ones and two-phase-write ones. MD-Read is the default strip-write AF engine in Linux kernel. ScalaRead and ST-Read mitigate the software overhead of MD-Read and thereby achieving higher performance. Read5F is an incomplete strip-write AFA implementation in SPDK. It can only serve read5 for strip I/O. I mean, the write size must be equal to the strip size, and also it has no crash consistency mechanism. So we considered it the ideal case of software-only solution. Finally, FusionRead is a SOTA two-phase write AF engine. In micro-benchmark, ScalaAFA outperforms other AF engines in all types of I/O access pattern, as shown in the black columns. For example, in 64 kilobyte sequential write test, ScalaAFA improves the write throughput by 2.5 times compared to FusionRead. Interestingly, Read5F, the ideal case of software-only implementation, outperforms ScalaAFA a little in 2+1 AFA, as shown in the slash columns, but has worse performance in in 4+1 and 6+1 AFAs. This is because conversion offloads is minor in 2+1 AFA, whereas becoming huge as the number of SSDs increases. In terms of latency, ScalaAFA shows significantly better CDF profiles in all scenarios. Red line represents ScalaAFA. For example, compared with fusion rate, ScalaAFA reduces the average latency by 53%. This is because ScalaAFA not only benefits from the high-performance user space storage stack, but also mitigates performance degradation caused by conversion with SSD internal resources, I mean the XOR engine. Also, ScalaAFA can achieve almost the ideal performance with only one thread for 4+1 AFA, as shown in the red line in the left figure. The superiority keeps in macro benchmark test. This figure shows the throughput in different real workloads. Higher is better. Red line represents ScalaAFA. As you can see, ScalaAFA achieves the highest performance in all workloads, and therefore it shortens the runtime by 2.8 times. To demonstrate the superiority of ScalaAFA on applications, we also conduct an end-to-end evaluation on RocksDB, a popular KB store with DB-Bench. Thanks to the utilization of SSD internal resources and the high-performance storage stack, ScalaAFA achieves the highest throughput in all workloads. For example, ScalaAFA outperforms MD rate by 41%. Finally, let me show the result of incremental test. Compared with fusion rate, ScalaAFA improves the write throughput by 58% for its user space log-free design. Further, the conversion of loading enhances the throughput by 38%. Before end this presentation, let me conclude our work. Existing AF engines fail to adopt high-performance SSD for the software overhead and AFA internal tasks. Tackling this issue, we propose ScalaAFA, an AF engine built from holistic designs, which deliver high performance at low CPU cost by embarrassing user space storage stack and exploiting SD internal hardware resources. ScalaAFA is open sourced at GitHub. Please refer to our paper for more details. That's all. Thanks for listening.